All right, so review for the probability test. I got to tell you guys, make sure you read through all your notes in the note spiral, rework every single one of the problems in the note spiral. I feel like these quizzes are I think they will set you up to do well. You need to make sure that you understand every aspect of what we go through tonight. If you have questions, please ask them as we go through or type them into the chat. So, a sporting goods store announces a wheel of savings sale. Customers select the merchandise they want to purchase. Then at the cash register, they spin a wheel to determine the size of the discount they will receive. The wheel is divided into 12 sections or 12 regions like a clock. 6 of the regions are red and award a 10%. The 3 white regions award a 20%, and the blue region, 2 blue regions, 40%. The remaining region is gold, and a customer whose lucky spin lands there gets a 100% discount, and so the merchandise is free. So, what's the probability that a customer gets at least a 40% discount? Well, there's a couple ways to approach this problem. So basically, at least a 40% means I have anything that's over 40. Well, it turns out that I have 3 of those. Very simply put, 3 over 12, 0.25. That's all you needed to show, okay? That's all you needed to show to receive full credit on that. What's the probability that 2 customers in a row get only a 10% discount? So we have 2 customers, so consequently 2 blanks, and when we look at the 10% discounts, and we have 6 of them, and so 6 out of 12, and they're independent, so the probabilities are not changing. Okay? And by the way, if you just have the 6 over 12 times the 6 over 12 and equaling the 0.25, Ms. Lamb and I are very, very thrilled with that, and I'm sorry I didn't have that up for you to see. The next one, what is the probability that 3 consecutive customers all get 20%? Once again, we have 3, so I need 3 blanks. All right, and the probability of a 20% is 3 out of 12. Once again, this would satisfy for the work shown. And I'm going to tell you that on our test, we're going to be looking for work shown, and then we're going to be looking for a decimal answer, and we're going to want it carried out to 4 decimal places. Okay. Number 4, what is the probability that none of the first 4 customers gets a discount over 20%? Well, there's a couple ways to look at this, all right? And what we're really looking at is the probability that that none of them get over 20%. So that means we're looking at the 20% and the 10%. And we happen to have 4 customers. So once again, 1, 2, 3, 4. And we end up having 9 that are less than 20%, or 20% or less, I should say, because we have the 20%, the 3 of those, and the 6 at 10%, so that's 9 out of 12, or 3/4. So 9 out of 12. Again, this satisfies for work shown. And by the way, on the quizzes that I graded, this particular page I was very, very pleased with. Very, very pleased with this page. And the question someone asked in the chat was, what if I left the answer in fractions on the quiz? That'll be fine, because I did not specify. I personally did not specify. I don't know if Ms. Lamb did, but I did not specify. So fractional response was full credit in my class. On the exam, we're going to ask you to show us work that looks like this, and then we're going to ask you specifically for a decimal answer, but we're going to be very specific when we tell you to do that. What's the probability that the first gold winner is the fifth a customer in line? So once again, 1, 2, 3, 4, 5 blanks. Winner, all of these are losers. Actually, they're not losers, they're just not winning the big prize. The probability of the big prize was 1 out of 12. So all of these are going to be 11/12, because that's the probability that they did not win the gold. What is the probability that there's at least one gold winner among the first 6 customers? This is the scary phrase. At least. Whenever we have an at least question, we're looking at a 1 minus scenario, and we have to work with what the opposite is. They're asking for a gold winner. We know that the gold winner's probability is 1/12. But because this is an at least problem, we're working with the complement. So 1 minus, and then we have 1, 2, 3, 4, 5, 6 blanks. And just to act, so you don't need to watch me write that, I'm going to just draw an arrow all the way across. And I end up with 0.407. So there's about a 40% chance that that there was at least one gold winner. Now, one other thing is I just happened to mention a percent. And if you wrote percents as your answer, that's also fine. So fraction, decimal, percent, but we are looking for the work shown. Otherwise, correct responses with no work is wrong. All right, correct responses with no work is wrong. I'm going to just pause this. I'm not going to stop the recording. So a city water supply system involves 3 pumps, the failure of any one of which crashes the system. The probabilities of failure are the pump are 0.025, 0.034, and 0.02. Assuming the pumps operate independently, this is an important phrase. They tell me they're independent, which means I can multiply them, all right? So it tells me they're independent. So what is the probability that the system does crash during the year? All right, so any one is another phrase of saying at least. This is another way of saying at least, in which case I'm looking at the opposite. So I'm looking at a 1 minus case because it's looking at least, and they're asking for failure. Well, remember, whenever they have an at least situation, I'm doing the opposite. So the opposite of failure is not breaking. So I need to work with a not breaking scenario. And basically, the probability this pump doesn't break is 1 minus that. So that's going to be 0.975. The probability this one doesn't break is 0.966. And the probability this one doesn't break is 0.988 or 0.98. Now, this section right here is actually the probability that the machine doesn't break. This is the probability the machine doesn't break. So if I have, in this case, 3 different pumps, I could have 0 break, 1 break, 2 break, or 3 break. They want the probability of at least, so they're looking for this. So if we do 1 minus the probability that none break, well, that's the probability that none break, and this is what we end up with here. So when we do that, we end up doing the calculation, and we get 0.076 and 9. All right, if you rounded, that's fine on the on the quiz because we didn't tell you what to do. But there we are, truncated. All right. Next one. There are 2 games involving flipping a coin. In the first game, you win a prize if you throw between 40 and 60% heads. In the second game, you win if you can throw more than 75% heads. For each game, would you rather flip 50 times or 500 times? So basically we have 40%, 60%, between 40 and 60 here, and then we have to be greater than 0.75. So 0.40 less than X less than 0.60. So that's what we're looking for. And we're trying to determine whether or not we're going to flip 50 times or 500 times. Well, this is a question that I really wanted to see the phrase law of large numbers worked in. I didn't necessarily count it wrong if it didn't, as long as the other explanation followed. But the fact of the matter is, we're looking for something about law of large numbers. And the law of large numbers says, as I do it over and over and over again, it gets closer and closer to the theoretical. Well, what is the theoretical? All right. So what are the theoretical? Well, the theoretical is 50%. So if I do it more often, I'm going to get closer and closer to 50%. This one doesn't want me closer to 50%. This wants me farther away or a long way from 50%. So law of large numbers says if I do it over and over again, this is going to become less and less likely. So consequently, I want to do this 50 times. And the more I do this, the more likely I'm going to be right in the middle between 40 and 60. So in this case, I'm going to want to do it 500 times. Now, I'm not taking the time to write out sentences on this one, but you basically should have said, for the first one, I want to do it 500 times because law of large numbers says it's going to approximate 50%, which is right between the middle of 0.40 and 0.60. Law of large numbers say if I do it a whole bunch of times, it's going to be farther and farther away from 0.75. So I want to flip it as few times as possible. So I want to do this the fewest number of times, which in this case is 50. Okay. On number 9, it is estimated 30% of all cars parked in a metered lot outside the city hall receive tickets for metered violations. In a random sample of 5 cars, what is the probability that at least one receives a parking ticket? Once again, we see at least, we know we're doing 1 minus, and basically we have 1, 2, 3, 4, 5 cars. So we can have 0 tickets, 1 ticket, 2 tickets, 3 tickets, 4 tickets, 5 tickets. This satisfies the at least. But because we know that all probabilities sum together, I can go 1 minus the probability of 0. All right, I can go 1 minus the probability of 0, and that'll be a much faster way of working this problem. So what's the probability that none of the cars receive it? Well, in that case, I'm looking at 1, 2, 3, 4, 5 cars. And since it's an at least, I need to use the complement, which is going to be 0.7. So once again, once I said earlier, once I get to the second blank, I usually get a little bit smarter. And I can use the exponent, and I get 0.8319. All right, on number 10, what is the following is from a particular region's mortality table. Nice. Probably should change mortality tables during COVID. That's probably not the best problem. So what is the probability that a 20-year-old will survive to be 60? Well, in this particular case, we sit there and go, you know what? They've already made it to 20. Okay, we already know, so we don't have to worry about this group. We're no longer taking it out of a population of 10,000. We're taking it out of the population of 9,700. There's 9,700 of the original 10,000. Well, how many make it to 60? 7,800. Okay, now I saw someone do this using a complement, and that was fine. All right, but this is the way I typically think of it, is saying, hey, you know what? We started off with 9,700. and we need to get, and we'll end up with 7,800. The reason being, we no longer have to worry about this part of the group. This part of the group doesn't exist, so we are now working with, hey, given that they've made it to 9,700. So essentially, this is a given that we got to 20. What's the intersection? And the intersection is 7,800. All right, we received a bunch of questions, and I'm going to pause this. Okay, so pinata scenario. A pinata is a container filled with toys, and candy is broken up then by hitting it with a stick. The drawing above shows Sophia trying to break a pinata. The probability that she will break the pinata on the first hit is 0.2. She'll continue to beat the pinata mercilessly until all the candy breaks out. If she does not break the pinata on a particular hit, the pinata is weakened, and the probability she'll break it on the next hit is 0.2 greater than the probability on the first hit. For example, if the pinata does not break on the first hit, the probability that it'll break on the second hit is 0.4. So calculate the probability that it does not break on the first hit and does break on the second hit. So first off, I'm just going to deal with the first hit. The first hit probability of breaking is 0.2. All right? You're like, well, gee, Mr. Spencer, they told me that. Yeah, they did. But now we have a second hit. So this is not breaking, and now this is breaking. So they told me this, the probability increases by 0.2. So 0.2 plus 0.2 is 0.4. But I need this not to break. For this not to break, it's going to be 1 minus the probability that it broke the first time, which is 0.2. So that makes this 1 minus 0.2 is 0.8. And I find out the probability that it breaks on the second one is 0.32. Okay, so that's my starting point. So if I have the probability of it breaking on the first hit is 0.2. Probability of breaking on the second hit is 0.32. That's a B, not a 13. That's a B for breaking. Please don't make fun of my Bs. I've had to grade all your writing. It's not nearly as bad as that. Trust me. All right. So the next one. So I'm going to write that down. 0.8, 0.4. And this was a not break and a break. All right. Well, now we have 3 hits. So it's going to be 1, 2, 3 blanks. This is going to be a break. This is going to be a not break. And this is a not break. Well, I know that it has to increase by 0.2. So this becomes 0.6 because it increased by 0.2. Well, I already have this not break. That's good. That's already a not break, so I can just bring it straight down. But I need to turn this break into a not break. So 1 minus the 0.4 becomes a 0.6. And so now I multiply that, and I get 0.288. So now we're looking at the fourth one. And we have 1, 2, 3, 4. Again, this is a break. This is a not break. This is a not break. And this is a not break. Well, once again, this has to increase by 0.2, which makes this 0.8. Well, this is a not break, so I can bring it down just the way it is. This is already a not break, so I can bring it down just the way it is. This is a break. 60% of the time it breaks, so the complement of breaking is not breaking. So 1 minus the 0.6 is 0.4. So then I multiply all that, and I get 0.1536. And I'm going to rewrite these up here, those same numbers. And label them. So this is not break, not break, not break, and break. And I should put the 0.1536 here. All right, so now we're going to go to the fifth and final swing because we're tired of this problem. I know you were. I saw the tears. All right. So once again, break, not break, not break, not break, not break. Once again, we're increasing this by 0.2, so this becomes 1. All right, this is already a not break, so 0.8. This is already a not break. This is already a not break. I need to change this value from a, because it's a break, to a not break. The complement of this is going to be 0.2. When I multiply all that out, I end up getting 0.0384. If I check my work, this all sums up to one whole. All right, it all sums up to one whole, which means I have a valid probability distribution. If I didn't do that, then I have a problem. There is partial credit awarded on this depending on what all you have. Okay, so calculate the value of X, show your work. Okay, so guess what? It's very simple. 1 times 0.2 plus 2 times 0.32 plus 3 times 0.288 plus 4 times 0.1536 plus 5 times 0.0384. And so that's my expected value. And I end up getting an expected value of 2.5104. Now, some of you are going, but if my table's wrong, then this is wrong. Yes, but whatever value you use in your table, if you use them here, you can still get full credit. And believe me, we'll check that. So basically, if you did this and you got it wrong, you can still get full credit here. Also, there's no reason that you couldn't have gotten this partial credit right there because they told you that one. Hopefully you got this one, and that would give you even more partial credit because we graded each one of these as an individual square, or that's why we're grading that. And that's why the points counted this. All right. And then, so now we have the expected value. It says interpolate. New word. Mr. Spencer's creating them all the time. At least this one is one that we can repeat, interpolate. So we're going to interpolate the expected value of X. And what this is, in the long run, in repeated sampling, if we did this over and over again, and we're looking for those phrases. If you do this in the long run, or if we did this over and over again, if we had someone actually wrote, if we had hundreds of pinatas, and they wrote that, that's perfect. Also, on average, we would expect it to take 2.51 swings. So in the long run, we expect it to take an average of 2.51 swings. There's no such thing as 2.51 swings. Sophia is never going to break it on the 2.51 swing. She may break it on the second swing, she may break it on the third swing or first or the fourth or the fifth, but it's never going to break on the 2.51 swing. So don't say we expect to break it on the 2.51 swing because that's false. On average, we expect to do that, or in the long run, we expect to do that. And we really like you to say things in the long run or in repeated sampling. We expect it to take an average of 2.51 swings. All right? All right. Pausing the recording. Actually, I can